Hello. So welcome to the session on vector algebra, and today will be the last session where we will be talking about triple product. If you remember, in the last two sessions we had been talking about product of two vectors, so that idea will be now extended for product of three vectors. And as we have seen, for two vectors there were two kinds of products, scalar product and vector product. In triple product also we will see two kinds of product, scalar triple product, and as usual the result will be a scalar, and vector triple product, so as per the name the result will be a vector. So first let us see scalar triple product. So for any three vectors ABC, scalar triple product is an expression of the form A dot B cross C. So that means first we are using cross product for the vectors B cross C. So the resultant will be a vector, and that vector is then again multiplied with the A vector using a dot product. And since at the last operation we are using a dot product, it is clear that our result is going to be a scalar quantity. And this justifies the name why this is called a scalar triple product. And this product is also sometimes called the box product and is denoted by ABC. And another thing, this expression A dot B cross C, we have seen that the answer will be a scalar quantity. Now that can be positive or negative depending on the set of vectors ABC is forming a right-handed system or a left-handed system. I hope we remember this term right-handed system. The vectors ABC will be said to form a right-handed system if, as we move from A to B in an anti-clockwise direction, then the C vector will point along the direction in which a right-handed screw will move. This we have seen in our last session on vector product. Okay, and now we will go over to the geometrical interpretation of scalar triple product. So what is that? This is a very interesting result, that the absolute value of the scalar triple product A dot B cross C represents the volume of the parallelepiped formed with the concurrent edges A, B and C. So how it happens? Let us see with the help of this figure. So here we have three vectors A, B and C over here. And now see, first of all, this B and C vectors, a parallelogram has been drawn here. So if we remember the vector product discussed in the last class, you will remember that the area of a parallelogram is given by mod B cross C if the adjacent edges are the B and C vectors. So here also, for this parallelepiped, the area of the base is going to be mod B cross C. And now for a volume of a parallelepiped, I hope everybody remembers the formula that the volume of a parallelepiped is given by area of its base multiplied with its altitude. So area of the base, as I just now explained, it is mod B cross C. And what is the altitude? Now this is the A vector. If it makes an angle theta with the z axis, then from our knowledge of trigonometry we can see that this height or the altitude is going to be mod A cos theta. So now what is the final expression then? Mod A multiplied with mod B cross C cosine theta, where theta is the angle between the A vector and the B cross C vector. Why theta is the angle between A and B cross C vector? That also comes from our previous session knowledge that B cross C will be pointed along this direction, perpendicular to the plane of B and C. So now finally, if you remember the formula of scalar product, this gives nothing but A dot B cross C. So in a summary, the scalar triple product A dot B cross C gives the volume of the parallelepiped which is formed with ABC as the concurrent edges. And This result basically leads us to another very important condition, the condition of coplanarity of three vectors. What is that? That is given by the following theorem. If three non-zero vectors are coplanar, then their scalar triple product is 0. Why this happens? This is very easy to understand if we just remember the result discussed in the previous slide. And if you remember, what are coplanar vectors? Coplanar vectors, of course, means that the vectors lie on the same plane, and therefore the volume of the parallelepiped formed by them will be obviously 0. So if the volume of the parallelepiped is 0, then of course the scalar triple product is also 0. And lastly, about scalar triple product, we see the expression in component form. So now if we have three vectors ABC which are given in the following way in the component form, like A is equal to A1i plus A2j plus A3k, B is B1i plus B2j plus B3k, and C is C1i plus C2j plus C3k, then the scalar triple product is given by this 3 by 3 determinant. The first row elements are the components of the first vector, second row elements are the components of the second vector, and third row elements are the component of the third vector. It's a very easy result to remember. So it's the 3 by 3 determinant A1 into A3, B1 into B3, C1, C2, C3. Now, why this happens? So this is now a homework for you. Try to prove it by yourself. And this can be easily done if you remember the expression for B cross C, which we had done in the previous lecture. So if these are B and C, write down the expression for B and C and then calculate A dot B cross C. You can easily get this answer. Also, from here, if you remember the properties of determinants, we also get some more interesting results, that A dot B cross C will be equal to B dot C cross A equal to C dot A cross B. That means we have just, you can see that we have just shifted the vectors by one place in a cyclic manner, and the result of the scalar product, triple product, remains the same. And this can be explained, as I have just now told, by the properties of determinants. If you remember that if in the determinant the rows are interchanged by one place, then the sign changes from positive to negative or negative to positive. And if the rows changes by two places, then the sign remains same. So if we just apply this property, you can easily get this result, a very useful result. However, if the order is changed, now one thing, if you remember, go to this line, you see that the vectors have been just shifted, but the order has been same. ABC, here also it's BCA, CAB, so the order is same. But if there is a change in the order, like if we talk about A cross C cross B, then there will be a change in the sign. And that is also very obvious if you remember the anti-commutative law for vector product, that B cross C is equal to minus C cross B. Okay, so with this, we are over with scalar triple product, and we will go to the next topic of vector triple product. So once again, if we have three vectors ABC, the vector triple product is given by this expression A cross B cross C. So that means we are first multiplying here B and C vector, and then that result is multiplied with the vector A, and in both the products now we are applying cross product. So obviously our final answer to the product will be a vector. And what kind of vector is this A cross B cross C? Where does it lie? That can be explained basically from this figure over here. So here again you see we have three vectors A, B and C. Now B cross C, the vector product, if you remember, the vector product of two vectors, that is directed along a direction which is always perpendicular to both B and C. That means perpendicular to the plane of B and C. And now A cross B cross C. So again by the same concept of vector product, because we are now applying vector product to A and B cross C. So A cross B cross C will be again now perpendicular to the plane of to B cross C. So therefore basically A cross B cross C will lie in the same plane as B and C. So this is the important result to be remembered over here, that A cross B cross C is actually coplanar with B and C. And therefore one can write this algebraic expression A cross B cross C equal to lambda B plus mu C, where lambda and mu are some suitable scalars. So what we remember from this discussion is A cross B cross C. This is our vector triple product, a vector quantity, and this is a vector which is coplanar with B and C. And now some important result which actually helps us to solve problems or rather to calculate vector triple products. A cross B cross C, that is equal to A dot CB minus A dot B C. This can be written in this fashion, that A cross B cross C is actually given by the product of the outer with the remote A dot C, outer with the remote with multiplied with the adjacent vector, minus outer again A dot B adjacent with multiplied with the remote vector. And one thing let us observe, the right hand side is a vector quantity because A dot C we are performing scalar product, so that is a scalar quantity. So scalar multiplied with a vector, it is a vector quantity. Similarly, A dot BC is also a vector quantity. So the net quantity is a vector quantity. So A cross B cross C is A dot CB minus A dot BC, which can be also remembered as outer dot remote multiplied with adjacent minus outer dot adjacent multiplied with remote. And how to prove it? Once again, this is a homework. And as a hint, I can tell you that use the component form of the vectors. So B cross C, you know how to write it in the component form. And I just try to recapitulate once. What was that in the component form? B cross C, can we remember? It was again expressed in terms of a 3 by 3 determinant, where the first row will be ijk, second row will be the components of the B vector B1, B2, B3, and third row will be C1, C2, C3. So write these expressions in the component form and try to get the answer. Okay, and as a corollary to this result, we can write some more results over here. Like if we have B cross C cross A instead of A cross B cross C, so we have just the positions changed. Now again we use this formula, outer dot remote, so B dot A multiplied with C. Now B dot A is A dot B, so it's just commonly written as A dot BC minus outer dot adjacent, so B dot C A. And the second one, A cross B cross C. Now see, this in the result, or where we defined also our vector triple product, we have written as A cross B cross C, and now this is A cross B cross C. Now although the order of the vectors are same, but are they same quantity? We are doing different kind of operations. Here first we are multiplying B with C, and then the result is multiplied with A. Whereas here we are multiplying first A with B, and then the result is multiplied with C. So let us see, does it give the same answer as the result given over here? Now first of all, A cross B cross C, using the anti-commutative law, it is minus C cross A cross B. So we have a minus C in hand, and now if we apply this outer dot remote formula, we will get this result. So if we compare now this actual result in green with this, the fast terms are same, A dot CB but in the second terms are different. So therefore, it shows that A cross B cross C and A cross B cross C, they are not the same quantity. So that means we should be very much careful with the position of the brackets in this case. Not that we can just change the position of the brackets because the order is same. Okay, so that is all for vector triple product. And with this only we will close this session on vector algebra, the module 6 of your bridge course. And one thing I should like to tell here again that as you will start your first semester, in the first semester course, you will have to learn vectors more. And this knowledge of this bridge course, the knowledge of vector algebra, will help you in that main course of study because there you will continue the vector algebra into vector calculus. Okay, so goodbye till then. Thank you.